little correction. Bridget does have a lot of impact, but it's not what she wants, the level. The making of the sausage and watching these billions of dollars kind of come through the bureaucracy can be very frustrating, and I feel that too. I'm Ken Wisian from the Bureau of Economic Geology. I do like interactive talks, so please ask questions at any point. I'm going to be talking about geothermal energy today, and I'm working on the assumption that no one here is a practicing geothermal person. It's been a small niche for many decades. So I did my Ph.D. in geothermal in the 90s, and the industry was largely flatlined until the last couple of years when it's really experienced a boom. And so I'll get into that. So what I'm going to do is do a fair amount of Geothermal 101. Please ask questions. Stop me if I use slang terminology or anything. And then I'll get into a little bit of current projects, how you explore for geothermal and that kind of work. So when I'm talking about geothermal energy, I'm not talking about ground return heat pumps for your house that are 30 feet down. We're talking drilling down to tap in various ways deep heat in the earth. Typically you're drilling hundreds of meters to kilometers down, and you're generating megawatts of power off of these systems. The U.S. is the world's largest producer of geothermal power at about, I think it's around 3 gig. But our grid is so large that it's less than 0.5% of our power supply, and it's all out in the western U.S. Some countries, Kenya, some of the Pacific Rim countries, Iceland, generate 25 to 50% of their power off geothermal. It's just a smaller amount. So I'm going to focus on electricity generation. Generally, you use a fluid of some sort that you circulate underground or extract from the ground, and use the heat content of that fluid to drive a turbine to generate electricity. Where's it coming from? Well, the core of the Earth is about the same temperature as the surface of the sun, but it's a lot closer to us. And on a continual basis, 44 terawatts of energy flow out of the Earth's surface and into space, just gone. That's a lot of energy. That's a few times more than the current world usage. But the huge amount is what's stored in the upper 10 kilometers of the crust. And a couple of studies have estimated that the extractable amount of heat in the upper crust could supply our total energy needs for several thousand years. So there's a lot to be tapped there. We have not even scratched the surface of geothermal power potential so far. To date, geothermal power is mostly in tectonically active areas. In the U.S., it's all from the Rockies west, where you either have volcanic activity or extensional systems that allow for very deep fluid flow in the crust of water, gets heated up, brought to the surface or near surface, like in Nevada and the desert areas, the Basin Range, or in the western U.S., like the largest single plant in the world. Oh, am I going? Yeah, there we go. Oh, it just doesn't show up well here. The geysers in California is the largest installation. It generates, thank you, generates 880 megawatts. It's got a rated capacity of about 1.3 gig, and that's based off a steam cap above a cooling igneous body. So two main styles you have in the U.S., extensional and then volcanic related or igneous related activities. And it's the same in all these areas. Till now, that's been a real strong limit on where you can do geothermal development. You have to go where nature concentrates the heat source in these regions. And so that's kind of kept somewhat of a lid on things, along with large upfront costs of geothermal power plants. The drilling particularly is a major cost. It's all up front. And unless you have incentives or end-to-end carbon accounting and credits, it's barely to not been able to compete with natural gas supplied power. Now that's changing for some reasons I'll go into in a little bit. I break geothermal power down into two main types, and I'll hit these terms repeatedly. Conventional and new paradigm are often called geothermal anywhere. To date, all geothermal power is conventional. What that means is you're tapping typically a hydrothermal fluid flow system in the ground, a naturally occurring one, and you're tapping that for energy. That's been done for over 100 years. The oldest still operating geothermal power plant is in Larderello, Italy. Been running, well, since the early 1900s. The geysers that I mentioned in California has been running since 1960. So a well-managed geothermal system, by the way, has essentially an indefinite lifetime. That's not factored into the pricing well either at this point. So 98% of them are hydrothermal flow systems. A steam cap, which is kind of your purest form, is very rare because it takes just the right geologic conditions to form one of those. There has been research for several decades on what's called enhanced geothermal systems. The DOE has sunk a lot of money into this research for several decades. And that envisions just stepping out around the edges of a known hydrothermal system where you still have hot rocks, but you don't have the fluid flow system, fracking the rock, flowing fluid through it, and getting it back up to the surface. It hasn't worked too well in that vein, but something very similar is coming on now, and that's the new paradigm geothermal. And for some technology advancement reasons that I'll show you in just a second, we are now right at the cusp of being able to drill anywhere and produce geothermal energy. You know, the crust gets hotter as you go down. It's a matter of how deep do you need to go, engineer your own fluid flow system to hoover up the heat and produce there. So we're right at the inflection point of a real revolution in this field, and it has gotten, pun intended, very, very hot. There is a lot of venture capital coming into this, a lot of interest from utilities. All the major oil companies have formed teams to at least watch the subject, and some are starting to get active in proof of concept and prototype projects. The naming system is still rather unsettled. This has only been emerging in the last few years. There aren't many publications on this yet. So you'll see a variety of other things. Advanced geothermal systems. Closed loop comes up a lot because that's a major aspect of these systems. But what's driving this is technology advances, which I'll show you in a second, and then also the worldwide drive to decarbonize, whether it's just a matter of policy or whether it's credits of some sort. Those are acting like an incentive for this, along with other renewables. One key aspect I really want to emphasize for geothermal, of the renewables that have the ability to scale up, it's the only one that's base load. Wind and solar, great, but they're not continuous. Geothermal is base load, and it can even be load following to an extent. And the utilities have started to wake up to that fact. You know, Texas rocketed to the lead in wind power with the right government incentives and such. And we've got a lot of wind, we've got a lot of solar, but no matter how much of that you install, you can't decommission anything. You can't decommission any existing fossil fuel plants because they have to be on standby for when the wind isn't blowing and the sun isn't shining. With geothermal, now the light bulb's coming on. If we can install geothermal, that's base load, we can decommission old stuff. So that light bulb is just starting to come on also. Any questions so far? I'll keep going. The new geothermal anywhere idea basically involves drilling down till you get to a temperature you want, and it's generally going to be 150 C, 300 F, or a little higher. The higher the better, obviously, but you want to get to enough temperature to justify to make it economical without having to go super deep, and the cost just goes up rapidly as you go deeper. When you get to a target depth, what you're going to be doing is one of two main approaches, either drilling a very long or complex radiator pattern in the ground so that you get a lot of surface area on your borehole so that you can conduct the heat into it, into a fluid you're circulating, Or you engineer a fracture system, either between two wells or around a well, and flow fluid, your own fluid, whether it be water or something else, through the fractures to absorb the heat. Either way, you bring it back up to the surface, run it through a turbine. Some key aspects to this, interestingly, it totally changes the exploration risk picture versus oil and gas or even conventional geothermal. Conventional geothermal, where you're going after a dynamic flow hydrothermal system in the ground, is a lot like oil and gas exploration. You've got to hit that permeable flow zone, and you may not know if it's going to be productive till you complete the well, and if you're off by 100 meters, you may have a dry hole. With this approach, you're not going to miss your target. Your target is that. It's a matter of how deep you need to go to get to the temperature you want, and can you make that match up with the right type of rock that you want? Yes, to make your target. Go ahead.
Are the drilling techniques essentially the same as oil and gas?
Yeah, the question is, are the drill? Yes, excellent. Is the drilling and the infrastructure the same as oil and gas? Yes, that's critical actually. And a nice aspect of this is probably 80 to 90% of the skill set, the hardware, the IP of oil and gas transfers directly into this. And in fact, that has the old school conventional geothermal players who have been small, it's a small industry, are quite apprehensive about basically being steamrolled if the majors jump into this. And I'll show you a little bit more about that in a second.
Does that involve horizontal drilling as well?
Yes. Hold that thought for just a second. There is with the fracking approach to this, or the long lateral approach, expected to be, and so far proven to be, far, far less risk of induced seismicity than fracking, or especially produced water disposal induced seismicity. And again, key thing, it opens up essentially most of the earth. Here's a map of the whole US, known geothermal systems out here. If you go deep enough, it's all hot, but you can still see that there's a lot of variability. And some areas are more ripe or are lower hanging fruit for early development than others. And that includes Texas, and I'll mention some projects I'm involved with here, particularly in the Gulf geopressure zone. But with the continuing advance in technology, we can envision essentially anywhere being open. Yes? And then, this is, it essentially is depth, but not quite. It's a rating that NREL developed, and it says relative favorability. So the red, it really is almost exactly depth, but not quite. There was over here.
Could you explain why there's a lower risk of induced seismicity for this?
It's using the same techniques, but it's at a much smaller scale, physically and temporally, and you're doing something different. I might get into a little bit of that at the end here, but a recent test project did produce no induced seismicity. One of the groups at the Bureau is also TexNet, which does the induced seismicity monitoring for Texas. We have 150 stations. We are all over the activity in the western part of Texas, including a 4.9 about a week and a half ago, which has become all too common lately. But we had an array set up around a recent test drilling project, which did do some of that fracking. Nothing observed above almost background. So very low. Okay. Why is this happening now? Why is there so much excitement and drive about this? Well, you kind of hit on some of that. It's the oil and gas drilling technology, whether it's the speed, the various supporting aspects of that, the accuracy. I mentioned that the conventional geothermal industry has been very small for a very long time. It hasn't had essentially any R&D budget. All R&D was done by DOE. The net result of that is that the technology used in the conventional geothermal world lags the oil and gas world by anywhere from a couple of years to a couple of decades. And the light bulb started coming on in people a few years ago. Hey, wait a minute, we can do a lot more here than they're aware of. Let's port that knowledge over into geothermal. So that's one key aspect of it. The other is advances in the conversion of heat to power. For the first 80 years of geothermal, and most plants in the world use water as your fluid. In geothermal, you just extract the water out of the ground that's there already. You bring it up to the surface, keep it under pressure, flash it to steam in a turbine, and drives the turbine. That's great for higher temperatures, but at lower temperatures, what's come on in the last few decades is called binary systems, where you run your produced fluid through a heat exchanger to an organic molecule, and that's called an organic Rankine cycle is the term for the generation. And that works better at lower to medium temperatures, like in the 200 to 150 C range. And that's become the standard for now for lower temperatures. What's coming on beyond that now is using supercritical CO2 as your fluid, both to mine the heat and to run through your turbine. And that promises double to triple the efficiency at the lower temperature range than the organic Rankine cycle. So that's a substantial change to the economic viability of these systems. So those two things coming together, along with the drive to decarbonize, are creating the opportunity for these new methods to extract heat from the ground. I'll show you a sampling of some of the styles of work that's being done. And by the way, the leading edge of this work rests in the startup field, in the startup world. It's not the majors. They're watching, but they haven't jumped in yet. So the startups, and there's about a half dozen of them, are really leading this charge, typically coupled with some academic partner. And I'll show you some of that in a little bit. And there's a spectrum of approaches that are out there. They all have great models. They need to prove it in real world cases. And we're going to see a lot of clarity over the next year or two as most of these startups do test their technology in an actual drilling and completion system. So the most common idea is something like this, where you have a well doublet, you flow cold fluid in, you run it across to the other well through a fracture system, you bring it up to the surface, you run it through the turbine, and then you put 100% back down in. That's why it's called closed loop. There's no venting to the atmosphere. It is zero carbon. So a huge factor there. So that's probably the most common approach, and there's variations on all these. The other end of the spectrum, or the most complex end of the spectrum, is something like this, where you essentially drill a complex radiator pattern in the ground, circulate fluid, down one, through all these laterals that connect at the end, back up. That's being pioneered by a company called Evor out of Canada. They did test drill kind of a single loop of this in Canada a couple of years ago, but at very low temperatures and shallow depths. They're looking to drill at producible temperatures and depths in the near future, and there's variations on their ideas. And then at the least complex end is this approach. I'm sorry, it's probably a little hard to see. This is from Sage Geosystems out of Houston, and their vision is to drill a single well with coaxial flow in it, and then frack out around the bottom of the well and create a natural flow system, bring the heat up to the bottom of the well, probably heat exchange it, and up to the surface. And there's variations on all these. A little bit more on risk. Well, let's see, I don't know if I really need to say much more on risk. Yeah, okay. Now, exploration. First of all, I know this is probably dating me. How many people even know what this is? Just a few, okay. Well, current geothermal exploration is really about this level. Jed Clampett out one day hunting for some food, shooting at some food or something, and up from the ground comes a bubbling crude. pretty much every existing geothermal power plant was sited based on surface manifestation. Walking the ground, or obvious things like geysers, fumaroles, mud pots, that kind of thing. Sometimes less obvious stuff like evidence of cooked rocks, typically bright colors like reds, yellows, greens, alterations to clays that tell you, yeah, there is or has been recently a lot of heat here. Let's drill down and see if we can really find some. I'll come back to that in a minute. The techniques involved, really there's a big break on whether you're going for the hydrothermal systems or the new geothermal anywhere style. The hydrothermal systems, there's still a lot of art in really finding those. Again, you're looking for typically a confined, tight fluid flow upflow zone. And you know, there's electromagnetics, MT, resistivity and stuff to try to find where the water is and where it's moving. The seismic doesn't factor too much into conventional geothermal. 2D seismic is almost never done, and 3D is pretty much unheard of in conventional. Geochemical is used a lot. It's cheap, but it has a lot of uncertainty on it. But sampling fluid waters that come up to the surface can give you an idea of what the maximum temperatures in the reservoir down below are. And you can see a variety of them here. Frequently, you'll have to do a lot of these different types and get a variety of numbers, and you kind of go, okay, well, under these rock conditions, I kind of think that one's more reliable. Structure is still a big deal. I've done gravity surveys to map out the structure in basin range basements, so you can kind of see, typically in the basin range settings, the fluid flow is up those basin bounding faults, and so you're looking for that structure to see where to drill on. That's conventional exploration. The new paradigm exploration is much more about old-fashioned geologic structure detective work. So I'll come to a project in a minute that we were doing in Houston, but a lot of the work was looking at 2D seismic, looking at old well logs and such, just to figure out what the structure of the site is. Where are there nearby faults that might short circuit your engineered system and such, along with temperature. And I'll go into temperature a little bit more in a second. Here is a map of Texas, estimated temperatures 10 kilometers down. So this is very, very deep, and it gets very hot at that point. This is 350 C at the top. The lightest colors are in the 100 to 150 C range. We already showed that there's a lot of variability here. And by the way, these are estimates. There's not any data as such from 10 kilometers. So this would be a first approximation map, but it gives you a general idea of what's happening. And at this depth, temperatures are just outrageous. I mean, if you can get there economically, you can produce a lot of energy because the amount of energy you can produce scales non-linearly with temperature. But the takeaway here is, you know, let's not go for 10 kilometers. Let's go for 5, which is a lot easier to do without pushing the technology limits. And so you can roughly cut the temperatures in half, and you're still well into a productive temperature of 150 C or better over a big chunk of Texas and the Gulf Coast. And I happen to have focused on DoD, the Department of Defense, getting them to be early adopter of geothermal technology because the first wave of this is going to be expensive. The estimates, depending on who you're talking to, on how fast geothermal anywhere will be able to compete with natural gas range from 3 years to 20 years. I think the lower end is probably more likely. But so I've gone after DoD as an early adopter, among other projects. But it's good for any critical infrastructure early on where you need uninterruptible power. You know, how many of you lost power during the snowpocalypse? I did. Some of that was because critical infrastructure lost power. Well, if you can site a 1 megawatt system or a 3 megawatt system near critical infrastructure, and geothermal never requires resupply because your resupply line is straight down. It doesn't have to come from a fuel tank that has to have electricity to be able to pump the fuel out. So some real advantages to this, and I don't really have a slide on this, but The size of these systems, a good geothermal well will produce 1 to 3 to 5 megawatts per well. You're not going to get a gigawatt scale power plant in one location because heat has a drawdown cone essentially the same as water does. So you have to space out your wells a little bit. But what I see happening in the future is a very different style of grid where you're siting medium to small sets of power generation close to need. Particularly, say, as the city expands, you might ring the outskirts of your city with geothermal power installations, and as it expands out, you keep going out. There's a lot of interesting nuances to how this will be implemented. Yes?
The cost analysis you're doing like 3 years, 20 years out, do they consider some of the indirect benefits and things or just direct?
This is pretty much direct. There's huge unknowns in like carbon credits that will affect it. That's probably the biggest single thing. And then how do you project out they're using the fairly standard decay curve of projecting out. Well, as we scale out, it should reduce, 20% for every doubling of installations kind of approach. So it's pretty simplistic at this point. And that analysis is being done by the startups themselves. We really need some independent, and there's a little bit, but it's kind of dated right now. So yeah, good question. It's really educated guesswork at this point. My analogy is if we really want to scale this up, what I look at is at the peak of the shale boom in Texas, we were drilling 15,000 wells a year. If you could generate a megawatt off of each well, if you're drilling that many wells, that gives you an idea of how fast we could scale up starting in a couple of years as these startups prove out their IP. There was, some time ago, an actual geothermal well in Texas funded by DOE in Pleasant Bayou up south of Houston. This was done late 80s, early 90s, and it did generate a half megawatt. This is a successful test. This was drilling into the Gulf geopressure zone and just extracting the hot fluids out of it. You also got co-produced natural gas, which actually gave a little bit more energy. But it has been proven. It was only funded and stayed in operation for 6 months. But there's a lot of potential along the Gulf Coast. I think that's a severe underestimate because that's dated and didn't use this new technology that's coming online. But there are projects brewing. So that well was right in this area. We have an Air Force funded project that's in design phase 2 right now, where UT is partnered with Sage Geosystems that I mentioned earlier to put in a 3 megawatt power plant at Ellington Field, a small military base on the south side of Houston. This is inside Houston city limits. If we can get to phase 3, which is a major hurdle to get DoD funding on the order of 15 million, matching the private side's already set. But if we can get to installation of this, it will get attention for its successful project that the same project in California or Oregon would not, because we'd be doing geothermal power in oil headquarters USA using a lot of oil and gas technology. Also, I think I've got a slide. Yeah, I've got a slide in a minute talking about a test well that was drilled just earlier this year. Some of the things that we're using on this, a lot of oil and gas data. This project is sited here at Ellington Field. This is the outer loop of Houston. Here's the inner loop between two old fields. So we can get a lot of data from this, a lot of structure data. There's seismic lines that cross all over here. And we've used that to, again, do old-fashioned detective work and build a 3D picture of what's the structure and the lithology at this site. My specialty is the temperature side. And on that, the main data source we got are bottom hole temperatures. Got lots of bottom hole temperature. If you've worked with it, it's very poor quality data. It is not the true temperature of the rocks because bottom hole temperature logs are run usually shortly after drilling completion. The temperatures are disturbed by the circulation of the drilling mud. And so you're always doing a lot of guesswork with how to correct BHTs. There are industry standard methods, Harrison correction, and some other variations on that. They are startlingly crude corrections to get to true temperature. It's not easy to do. I've got a summer graduate student seeing if some machine learning can improve the picture any, but the biggest problem is the amount of information you have supporting a bottom hole temperature off a well log is skimpy. What I hope to really get out of this is going forward, for very little cost, if we can get people to record this data and this data and this data, then BHTs become a lot more reliable. So individually, no BHT is reliable. But if you can aggregate them in a large scale, you can get something that starts to become something you can rely on. So this is a sampling of bottom hole temperatures in this area. And at a rough approximation, you can see a pretty strong linear trend. There's actually variation in here that reflects the geology. But you can see a good enough trend to know that for this project, where we want to get to 175 C or so, we're going to need to drill down to about 5 kilometers. And that's a pretty reliable estimate. Yes?
The green circle right there, just under the Deer Park.
Oh, okay.
What is that?
I have no idea. This is an industry data set, proprietary data set that we bought access to. I'm not an oil and gas guy, so I don't really. What I was interested in was the BHTs off these wells. Right there. Well, truth in advertising, I have a little bit of inside info because I used to command this base. Okay, you're welcome. So that's the temperature there. Let me see where I go after this. Oh, the structure. This is just simplified, but just shows you where in the big scheme of the huge sedimentary wedge of the Gulf Coast that this lies. One key aspect to here that we can take away is drilling to 5 kilometers. We're nowhere near the basement, so it's all soft rock, relatively easy to do. Yes.
So you said a lot of the geothermal is based on fracking the rock and, getting some fluid flow. Is that if you're still in 5 kilometers down, you don't have to do any fracking, right? The water flow,
Through the porous media. Okay, so do you even need to do fracking at that depth? Most likely, there are options for just if you've got a highly permeable zone, you can flow through it, but that makes it difficult to do the closed loop. We're actually, in these kind of approaches, you're actually looking for a tight rock with no permeability. If you go for a highly permeable zone, that's a different approach. It's much more like the conventional, and that is actually pretty low-hanging fruit all along the Gulf Coast, because you got the, well, yes, but more than likely what you've got is fluid in place. So the lowest hanging fruit is actually with no advance in technology, just drill into the Gulf geopressure zone in a permeable area, produce the fluid out of it, basically like an oil or gas field. It would be, you'd be extracting it one way, 20-year lifespan. But that is doable, and that's basically the approach that Pleasant Bayou test well took, was just produce the fluids out one way. But if you're trying for these closed loop systems, you really don't want to touch that stuff. You don't want to have to deal with formation fluids trying to push their way in. So you're really looking for tight rocks that you can engineer your own system with. Follow up?
Are the turbines able to extract heat out of salt water the same as fresh water, the same as other fluids?
It does matter a lot, because when you're dropping the temperature and pressure, you're taking all kinds of stuff out of solution. In the conventional world out in the western part of the U.S., scaling, as it's called, is a major source of your O&M expenses, because you frequently will deposit a lot of silica or calcite in the piping on your turbine blades and everywhere else. So the maintenance of that is a major factor. There's a lot of chemistry that's done to inhibit scaling, but it does add to the cost. That's another advantage for going for the closed loop because you're using your own designed fluid, pure water or otherwise, whether it's pure water or organic molecule or supercritical CO2. Yes?
Talking about the supercritical CO2, is that, are they offering that as like a potential carbon sequestration thing? How much fluid does it take, like, and where would you pull it from?
Yeah.
Do you extract CO2 from the atmosphere and then like?
Fair. Okay, so with supercritical CO2, is it carbon sequestration and where are you getting it from? Both good questions. Where you're getting it from will be probably an industrial supplier of CO2, Air Liquide or someone like that. Technically, yes, you can say it is slightly carbon negative, but the volume of your circulation system is not that big. It's not the megatons, gigatons that our Gulf Coast Carbon Center is working projects to sequester. But yeah, for PR purposes, it's slightly carbon negative.
I mean, I guess if you're scaling up the number of them, though, eventually you.
It could start to have impact. Yeah, that's a good point. That's a good point. A little bit more on temperature. The gold standard of temperature at depth is an equilibrium temperature log, a high resolution equilibrium temperature log. This is one I did back in my graduate days. Still good data. And what you get is readings typically every few centimeters to 1,000th of a degree accuracy. And you're doing this in a well that's been dormant for hopefully a couple of years. That's obviously rare. People don't just leave wells open and unproducing for a long time. But when you can get into one and log it, it's worth its weight in gold for calibrating BHTs, doing other things. Yes, sir. Oh, okay. Ooh, I got to move quick. Okay. As a byproduct, you'll notice if you take the derivative of a temperature log, you can get a lithology log. It tells you a lot, as good as many others if you're used to using it. Okay. I can skip those BHTs, it's the same thing. Okay, this is a test well that was drilled this year in far South Texas in Starr County by Sage Geosystems. We supported them with the determination of the lithology and structure and a seismic array actively monitoring the drilling project. What they did was they re-entered a dry hole gas well, and it's right down this region, and tested their IP, which is what I mentioned earlier, the fracking out, down, and around the bottom of a well. So they were able to frack a vertical fracture, or create a vertical fracture 3,200 feet tall, and then do several types of experiments on flowing through that fracture and extracting heat out. And did that with no induced seismicity. That was pretty substantial. And I'll boil it down to the net result. They tried flowing, this way, they tried flowing that way, and they also tried essentially huff and puffing, just pushing in and then letting it flow back out. The most efficient approach on this proved to be the cyclic method, pushing fluid in, didn't have to wait for long, then letting it flow back out under its own pressure from the fracture wanting to close, and got pretty good output of the heat. So they're thinking now about, well, maybe you stage wells, kind of like an 8-cylinder engine, and you just alternately fire each of these one at a time to get a continuous process of output. So that's a very new, very different idea. They just announced this last week at the Pivot 2020 conference. And by the way, if you're interested in geothermal, there's two main conferences. One is Geothermal Rising, which will be in Reno in a couple of weeks. But online, free, that you can watch all the recordings of, are the past 3 years Pivot conferences. Google Pivot 2022. I think the recordings are up by now. And you will find a talk about this technique. I didn't put this slide in the packet that you can get because they have talked about it publicly, but I didn't specifically ask if I could release this. But you'll find it online at a recording of the Pivot 2022 conference. So a lot of new, exciting aspects of this. I'll just mention briefly. There are other things you'd expect to find in any kind of drilling operation, But particularly because we're going to be siting close to need, and in our test project inside the city limits of Houston, we already have a seismic array there collecting background information that goes right to our public TextNet website. So I think it's critical in avoiding the NIMBY issues to be open and very clear on our seismic data on these projects going forward. In Europe, projects have been stopped cold for a magnitude 3 in days, just stopped. In Texas, we've had a whole bunch of magnitude 4s to 4.9s in West Texas for several years now. Now it is starting to get people excited, even in Midland, Odessa, but it's a different situation. Okay. More questions until we run out of time. It's a lot to throw at you. It's an exciting field. It is very dynamic. Tons of private money flowing into this right now. Yes?
When you push, you were talking about the huff and puff method. Do they push with air or do they use more fluid?
Fluid. This was done just with water. Future tests probably will go to supercritical CO2. First year, then there. Yes, sir.
How does consideration of substance affect design?
Mm-hmm. Good question. So how does subsidence affect this? In the conventional world, it is an issue. And generally, when you're producing a hydrothermal system, you re-inject as much of the fluid as you can back into the ground, mainly to keep the pressure support up on the reservoir. I'm not aware of any significant subsidence issues, but there is a little bit because you're net withdrawing. In a conventional system, you are net withdrawing fluid from the ground, so it'll be the same as any other water well type of system. In the new style, the new paradigm systems, it isn't an issue because you're not producing anything from the ground. You've drilled, but you're circulating in closed loop. There is no subsidence. Where was it over here? Yes, sir. Another excellent question, and I get asked that by various oil companies on a weekly to monthly basis. There's strong interest in that for obvious reasons. It's a big unknown at this point, and the research hadn't gone as far in that area as others. But, for instance, re-entering that old gas well, they had to do some reworking, and it wasn't that old a well. So I think there's going to be a major factor of how old the well is, obviously the conditions it's in, whether if it's an acidic condition or something. My hunch is that greenfield drilling in an existing field where you at least know it is probably going to be better, but it's to be determined. I would really like to do some projects in West Texas to test that out a little more. And there's other ways to use geothermal too that I didn't touch on here, but one of the other projects that I'd like to get funded is to do a geothermal well right next to a wind turbine and look at taking peak energy off of the wind turbine when it's not being used and using that to mechanically and thermally inject into the ground and use the earth as your battery. Now it's obviously not going to be super efficient, but talk about scalability where you have overlapping old oil fields and wind turbines, and the fact that it's a lot better environmentally than big battery banks that have strong impacts. There's a lot of variations on this. I've gotten one call from a Bitcoin miner wanting, well, I'm being pressured to get off the grid. Can I do geothermal power for this? Yeah, you can. It's probably not the cheapest source at this point. There's attempts to get a geothermal desalinization plant going in McAllen. A lot of different uses for this. Yes?
For the sites that have geothermal potential as a centroid, how far out can you spread that capability, whether to another area where there isn't and move it over?
Okay. In conventional hydrothermal, it's pretty limited because you've got to hit those upflow zones. In new paradigm geothermal, it's unlimited. The temperature variation in the rocks is very gradual. So, the temperature at 5 kilometers here versus 1 kilometer over there is going to be the same, unless there's a strong structural break in between. So, yes, you can. It's really a matter of how big an area can you get the surface and subsurface rights to? I'm looking at doing a study starting later this year on the potential of converting decommissioned coal plant sites to geothermal production. I think there's a lot of potential there. You already have some sunk infrastructure. You've got presumably all the rights you need, and that's a whole different subject. By the way, there's also formed up earlier this year Texas Geothermal Energy Alliance. It's an industry association led by Barry Smitherman. Y'all might know that name. He's a former commissioner of Railroad Commission and TCQ, I think. So it's an industry association. Their two main goals are education and getting the legislature this next session to very clearly define who owns the heat. You can't ignore that issue. If it's water you're producing out of the ground, that might be water rights. If it's heat, is it a mineral? Is it something else? If it's just the heat in the rocks. In the western states, that's already been settled, but obviously it's a state-by-state issue. They've got some pretty good weight behind them, so I think they'll be successful in getting clarification next year.
You brought up you have some sources of funding.
Mm-hmm.
What industries or so forth?
Okay, what are the sources of funding? There's still, DOE is still a big player in that, and they really didn't get much of the infrastructure money, but they have a pretty healthy budget anyway, and they're starting to release some calls for proposals. So that's one source. There is a lot of private venture capital in this area right now. That's probably the biggest driver. The majors are, again, interested in, there's a spectrum from, prove it, to, yeah, we want to do some test projects on the majors. And there's a small trickle of acquisitions by the majors and other similar types of companies like Schlumberger and the service companies and such, of some of these ideas on this new paradigm. But it hasn't really taken off yet. I think eventually, yeah, these startups will probably mostly get bought out by the major energy companies and producers and such. So we got that. A little bit, I did a major part of a study that's in final editing now that was funded by the Mitchell Foundation. So private foundation funding to really assess the geothermal potential of Texas. Hopefully that'll be out in the next month or two. And that's like, the total is like a 300-page report that includes policy, economics, and other things. And we've got about 100 pages just on the resource. So it's an interesting mixture of funds. Pivot 2021, last year's conference, Richard Branson was the keynote, and that was like 5 days after he went into space. You also have, I think it was Google signed a major geothermal power contract with one of the startups last year. So a variety of sources.
Implementation.
When can we expect to see these? Well, you'll see prototypes and proof of concepts now and for the next couple of years. Once those are done, once it's proven, I think you'll see a rapid takeoff of actual commercial projects. And actually some of these, there are prototype/commercial projects brewing in multiple parts of the U.S. I know of a couple that I'm hearing things about in Texas, again, along that Gulf geopressure zone. So 5 years from now, I think you'll see multiple working geothermal power plants east of the Rockies with a rapid increase following that. Yes?
Are there any countries leading the way in this that make their power mix maybe not predominantly geothermal, but has a proportion geothermal?
Remember that map of the tectonically active areas of the Earth? The Ring of Fire has long been a major area of geothermal production. A lot of the countries around the Pacific get a sizable percentage of their power, and this is all conventional geothermal, the hydrothermal system. So they get a lot. I mentioned Kenya's come on real strong in the last 10 to 15 years, from basically zero to half their grid coming off geothermal. That's in the African Rift. Iceland is a big one, and Iceland is one of the few countries that has a really, outside the US, that has a really strong geothermal academic program. By the way, there's not many programs in the US, even worldwide, to have that. So Iceland, the Netherlands is fairly big. Germany and France do a lot in this. England is starting to do more. Turkey is scaling up. South America is severely underdeveloped in this area. They have a lot of resource that just hasn't been developed. There are projects brewing. There are projects brewing almost everywhere right now. But that's a major underdeveloped area, I think. Good questions. Keep them coming.
So you talked about the Gulf Coast being the prime area for geothermal extraction. How about Big Bend area, foreseeable from
Uh,
like candidates?
yes. Now, if you go all the way out to El Paso, I think that's really good. It's actually on the edge of the Basin and Range high heat flow area. And there were some test wells for a military project done like a decade ago. The project didn't complete, but I've been able to look at those logs, and the temperatures look pretty good to me. Now, along the Rio Grande Valley, the whole border area, there are indications that there's good heat there, but the data is very, very sparse. That map I showed you earlier, estimates of temperatures at 10 kilometers, showed a lot of heat there. But that's an area I really think needs to be proven more. One of the other projects I'm doing at the Bureau right now, and it's unfunded by anyone outside, so I'm doing it at a trickle, but going through Texas county by county, compiling all the bottom hole temperatures, updating the maps and the estimates of the temperature so we can get a better picture of Texas temperature at depth, county by county. I'm hoping to get that actually fully funded so I could do it in less than a decade at some point here.
Well, good. You said a lot of geothermal work is done by startups, and how big are these companies? What types of jobs are there?
Okay.
Are they mostly, around engineering and turbines and construction of
Yeah.
facilities, or is there a lot of geoscience needed in the market?
Yes. So in these startups, what's the job market? What's the capitalization look like? Most of them have done one or two fundraising series, usually with no shortage of investors, in the low tens of millions of dollars range. Some of them are getting up into the 100 million now. These startups are each really being driven by an engineering approach, a set of intellectual property on how to do that mining of the heat. About half of them have no oil and gas background, and about half are old oil and gas people transferring their knowledge in. You see a big difference in how much they think they need geology by that background. If you're coming from oil and gas, you know the curves that Mother Nature can throw you, and you need to know as much as you can. I liken it, having been a flyer for decades, to no matter how good your technology is, you still want to know what the weather is at your destination for landing. You still need to know what the rock is in every way possible, what the temperature profile is. So yeah, you're not going to miss your temperature, but what if you have to go 50 meters deeper to get to the temperature you want, and that puts you in a formation you didn't want to be in? So yes, there is that. They are all hiring at a moderate clip. They're all growing. And there is a real shortage of actual geothermal expertise in the world. It's been such a small niche for so long that the demand for people who actually know geothermal is just off the charts. Myself and some others did a one-day seminar, kind of expanded Geothermal 101 for AIPG last year. We're looking at expanding that to a 3 or 4 day session. There are some other folks that are kind of starting to do this to give especially practicing geologists that transfer in to this. So pretty good time, I would say. It's going to, assuming we don't hit any unexpected roadblocks, which is obviously a big if, I think you're going to see a real boom in this that will be at least as big as the shale frac boom. At least, if not world-changing on the energy picture. The only other real competitor I see for this type of energy is small nuclear reactors, small modular reactors, which is a great technology too, but has obviously its own drawbacks. But for baseload energy that doesn't emit carbon, those are your two main choices. I think I'm about out of time. Well, do I have time for one more?
Sure.
Okay. Okay. Generally, well, if you're talking conventional geothermal, for instance, that geysers that I mentioned, the geysers field in California, actually covers about 100 square miles, has 12 or 13 power plants on it. That's the biggest you'll find anywhere in the world. Most of these are typically a couple of square kilometers in area. They'll have a handful of wells that all feed into a power plant in the center. That's all conventional geothermal. With the new paradigm geothermal, what you will have is a drilling rig. Once the drilling rig is gone, you put the power generation right next to the wellhead. And especially with supercritical CO2, the generators are about 5 to 10% the size of a water-based turbine. So they're much smaller. So for instance, that 3 megawatts that we want to install in Houston, it'll be 2 wells just off the same platform. And the space for the generation will probably be about this big. So very small footprint, which also feeds into that, putting the generation next to need, working it into city planning, those kinds of things. Okay, I think I better stop there so y'all get a little bit of a break. I'm at the Bureau. If anyone has follow-ups, you can find me online easily enough. I've got to head back to my office in a minute, but I'll stand outside for a couple if there are a few other questions. Thank you very much.